Now to C, which is fortunately a short one, we now want to try and consider a specific case where the claim sizes are assumed to be exponentially distributed with parameter theta. So let's just write that up here. We assume the claim sizes are exponentially distributed with parameter theta. Now what we want to do is to find the adjustment coefficient R in order to be able to have some expression for the shifted measure. So find the adjustment coefficient R. Now recall that R, by definition, must satisfy that the cumulant generating function evaluated in minus R is equal to 0. So in order to find that, we should calculate the cumulant generating function, or something that is just as good, because the cumulant generating function in minus R being equal to 0 is equivalent to the moment generating function in minus R being equal to 1, right? So it is just as well if we can find the moment generating function in our case. Let's try to find the moment generating function of just alpha. So in general, so the moment generating function of Z1 is given by the mean value of e to the alpha, then we just plug in c tau 1 minus y1. Now since we're in the Kremer-Lundberg model, we have that tau 1 and y1 are independent. So what we have now is it's just the product of the mean of e to the alpha c tau 1 minus the mean value of e to the alpha, oh, not minus, sorry, multiplied by the mean value of e to the alpha y1 with a minus in the exponent. And that is equal to the moment generating function of tau 1 evaluated in alpha c multiplied by the moment generating function of y1 evaluated in minus alpha. Now both tau 1 and y1 are exponentially distributed, so just recall that if you have an exponentially distributed random variable, so for an exponentially distributed random variable with parameter beta, for example, the moment generating function in alpha is given by beta divided by beta minus alpha. That is just a very useful little reminder to keep with you. So therefore, we can calculate the moment generating function of Z1 by considering, well, the parameter in the distribution for tau was given as lambda, so it's lambda divided by lambda minus alpha c, and then for the moment generating function of y, you have theta divided by theta plus alpha. And what you want to do now is to find out what the moment generating function is in minus r, so we just replace that in the above. It's lambda divided by lambda minus alpha c, where alpha is minus r, so plus rc, and then you have theta divided by theta minus r. And you want to set this equal to 1 and solve for r. After you've been solving for a bit, you should arrive at the fact that 0 is equal to cr plus lambda minus theta c, which will then imply that r is equal to theta minus lambda divided by c. And also note that very conveniently, due to the net profit condition, which tells us that c is greater than lambda over theta, well, then this thing here is also greater than 0. You can realize that by moving things around a little bit. So we now have an adjustment coefficient, and therefore we also have a means of finding the distribution of a variable under mu tilde, which we will do in the next exercise.